talk today, I will present you improvements we have done for the integrated fatigue analysis in PERMAS version 20. So, just 3 points, a short introduction and overview. Then for the second part, I will introduce you some of the improvements and news we have done for the fatigue module and give you in some more details 2 examples on how you can use these things. And then, of course, a short summary. So, the PERMAS Live module was introduced in the PERMAS version 19, and the development was done in cooperation with STZ Verkehr, the authors and developers of the fatigue software WinLive. And the approach that we have focused on so far is a stress-based high-cycle fatigue analysis that analyzes data in the time domain. So we can handle multi-axial stresses that may occur if you have non-proportional loadings. And so far we computed damage values for solid elements, which we now extended in this version to also include shell elements. And furthermore, we provide you with additional results that you can use for verification purposes. So this is now the second talk on fatigue, so by now you probably should be familiar with what fatigue is, but still let's do a small definition for the purpose of this talk. So fatigue is a phenomenon that has been studied for well over 150 years now. And the observation that describes this fatigue phenomenon are that components that were in use for a long time may suddenly fail. And this failure is not caused by overload, as the load is well below the normal static yield limit. But instead, the load varies over time and is often repetitive. So it's the constant loading and unloading, so the forming of stress cycles, that is the nature of the fatigue phenomenon. So, as we've already seen in the previous talk, we also think of it at the moment as a black box where on the left side you put in your model and your load and therefore your stress history, and you get out your damage that is caused by this load or stress history on the component and part. So a little bit more in detail what is in the black box that we saw on the previous slide. So if for the moment we fix a point on our model and we use think of what this point is observing, then we have a tensor-valued stress history, and now we fix a cutting plane and compute a scalar-valued stress history, which is some function of the shear or normal stresses that is acting on this cutting plane. Then we get this kind of signal. And this we can now do what is called a cycle counting. We do this with a rainflow algorithm, and what we end up with is a stress spectrum. You can see it down here. And now we have to account for the non-zero mean stress, which is done by amplitude transformation. And this now stress spectrum with a mean stress 0 can now be used with our local SN curve to compute the partial damages. And then we repeat this process for the next cutting plane. And in the end, you will end up with a damage result that is the maximum values over all the cutting planes. Okay, so in the second part now, I will focus a little bit on the improvements we have done and what you can do with this. So first of all, we improved the usability by introducing an SN curve generator, which follows the FKM guideline. So for you, this means you have a simplified input. You now have a new dot key, which is $SN curve FKM, which replaces the former $SN curve and $SN param. You just define one SN curve for each material, which hopefully is less error prone. And what you have to do is let's say, for example, you want to define a SN curve for a nodular cast iron. Then you take your U455 user manual, you look up in this table on the right the case of nodular cast iron, which gives a material group of 12. and then you enter this in your header line here, and then you provide the ultimate tensile strength, the yield limit, and the stress range of dispersion, so some statistical information. And this defines you then the blue SN material curve following the FKM guideline. So once you have this blue material curve, then you also need your local SN curve, which means that you have influence factors that may vary over your model and which may, for example, depend on your surface finish or may depend on the local loading conditions and therefore the geometry. So for the example, the support factor. And with this, you get your local SN curve. For verification purposes, we now introduced new results that you can use to verify on how this new local limit is being computed and to better understand what the influences of each of these individual influence factors are. Another thing that we provide you now with is a further result that we've shown here, which is the fatigue stress collective info, which gives you a simplified view on your fatigue stress history for one critical plane. So you get a lower and upper bound, for example, over all the time values for each point in your model. As you already may know, to do a fatigue analysis in PERMAS, you can use, or you have to use the generate fatigue command, which produces a secondary result. And one of the things we had in mind when we implemented our fatigue module is that you can do multiple fatigue analysis within one job, and especially within one situation. So down here you see an example where we're doing one static analysis followed by 3 fatigue analyses. And each of these fatigue analyses will, in this case, give you a new result column. And so the question you may ask is, why is this useful? Our motivation for this was that we thought it's easy for comparison of different fatigue analyses. And especially if it's done within the same task bracket, you do not need to repeat the primary analysis, so it's rather efficient. Then the question, of course, arises, why would you want to do this? And one answer to this might be that you still are in a phase where you can explore design variations. For example, you can change the material that is associated with your point of interest, which was already possible within PERMAS version 19 without repeating your primary analysis. And now we also extended this that you can alter any of the local properties, for example, the surface roughness. And the second reason that might come to mind is that it might be necessary to do multiple fatigue analysis in one situation because you need this to handle a complex fatigue load. And for this, I have an example here that you already might have seen if you remember the talk this morning, where we also showcase this example. So this is an example of differential housing that is from a truck's powertrain. And what you want to do is you want to understand what the damaging effect of a driving situation is for the stresses that are induced on the differential housing for the rotating load that you're seeing here on the outer ring gear. So what you want to do is you want to analyze the stress history for different torque levels. So what you do is you do one static analysis to compute a time history for one fixed torque level. And then within the fatigue analysis, you can define these scaled stress history values that you've seen here, where you take the stress state at the end of your assembly phase, subtract this from your stress history that you computed once for a fixed load level, then you scale the difference and afterwards add the stress state again onto this. And if you do this, you can do the, in this case, the 70 fatigue analysis within the same situation without repeating your primary analysis. So what you end up with is what you see here. You end up with 70 results which represent the damage that you get for one revolution for each new torque level. So now if you have a driving situation where you're giving the number of revolutions for each torque level, then you can compute the total damage just by taking your damage for one specific torque level, multiply by the number of revolutions, do this for all the other things, and sum it up. So again, this is one load collective that you apply afterwards in another fatigue analysis, which then gives you your total damage. And if you think now that you might have different driving situations, you might have different load collectives, which you then, so to compute the damage for each new load collective is just to apply one additional fatigue analysis, which recombines the damages of these 70 individual fatigue analyses that have been done before. So this might be another good reason why it's useful to have the ability to do multiple fatigue analysis within one job. Another aspect that I would like to talk about is the efficiency that we had in mind. So we already in the PERMAS version 19, the fatigue command handles automatically any of its prerequisites. You see down here in the example, again, you do a static analysis followed by generate fatigue analysis, generate fatigue command, and then afterwards you can directly export your damage. So the fatigue command by itself takes care to compute the nodal point stresses or the nodal point stress gradient if you require them. And this, in case, may depend on first computing the element stresses. So what we have done now is that we ensure that this is only done on the partial model that you are interested in for the fatigue analysis, which means for you that we have now minimal disk space requirements and we only compute what actually is needed for the fatigue analysis. So how does this apply, for example, for a modal time history? So if we think about that we want to handle very large time history jobs, then there are at least two enemies to this, which mostly is disk space. And so what we have come up with is the idea that is following what we have done for the modal time history statistics, as some of you might know that are doing dynamics. So we do not store any results in the time domain. So the biggest thing that we would have to compute is the stress history, which is, as you can see here, on the order of the number of your fatigue nodes times your number of time steps. So the number of time steps may be well in the several hundred thousands, and the number of fatigue nodes depends on what size part of your model you want to analyze. So this is already never stored. It's instead computed row by row, and then once we've computed a row, we can analyze the stress history for this and go on to the next row, etc. But still, the disk space is a limiting factor because we also, for this approach, have to include the transformation matrix from the modal space back to the physical space. And this matrix is normally of order of your degrees of freedom times your number of modes. And then furthermore, you also have to store your modal stresses, which is the stuff down here, and some more objects that we need to compute beforehand. And these are all of the order of your number of fatigue nodes times your number of modes. So if you want to increase your number of modes, your transformation matrix might easily be a problem for you, or if this is not the case, then probably the modal stresses will overflow your disk. So we can now use the new MLDR feature that you have seen here being talked about, I think it was this morning. And this new MLDR feature eliminates the need to store this transformation matrix. So the first enemy is already gone. So now what can we do about the rest? It still might be the case that you have a large portion of the model that you want to analyze. So the number of fatigue nodes may be the problem, especially if you want to increase the number of your modes. So in this case, what you can do is you can use again the possibility that you can do multiple fatigue analysis within the same situation, and you can simply just use what we would call a one part at a time approach. So you can do several fatigue analysis now for just a part each, which then reduces the amount of storage that we have for one point in time to reserve to compute the stress history. So an application of these things I would like to showcase now on this model that you already have seen being mentioned at least in 2 talks today. So it's again, what we've done now is, as we extended the fatigue analysis for the shell models, we included the truck chassis side rails as part of this complete truck chassis. And you see we have about 82,000 fatigue solid nodes, which are for these springbok down here. And then we furthermore have about 54,000 fatigue shell node pairs, but you have to double this number because we have to do an analysis for the lower and for the upper part of the shell. So this means that in total we have about 190,000 fatigue nodes that we need to analyze for, in this base case, 550 modes. And this is done in 16 different situations for 16 torture tracks with a total of 174,000 total time steps. So what you see here now is, if we focus first on this picture here, you see the elapsed time on the horizontal axis, and you see the frequency limit on the vertical axis. The dark part is the classical part with a subspace iteration for the vibration analysis. So you see if you increase your frequency limit from 49 to 100 to 200, you increase the runtime from about 7 hours to more than 12 hours. At the same time, you increase, if you have a look at these 3 bars, the amount of disk space quite dramatically. And in this last graph, you see the disk I/O that we have to do, which goes down from 50 terabyte to about 150 terabyte. So if we now change the vibration analysis to use the MLDR solver, we can reduce the runtime already for this low frequency limit by more than a factor of 2. And if, again, we would now increase the frequency limit, you see that the elapsed time gradually increases, and which gives you an even better speed up compared to the classical subspace iteration variant here. And at the same time, you see the disk space barely increases and stays well below 1 terabyte. And the same with the disk I/O. And if this still is a limiting problem or a limiting factor for you, you can now use this one part at a time approach. And so if we now do two fatigue analyses. So the first is fatigue analysis for the sidewalls and the shell elements, and then the second fatigue analysis for the solid elements. In this case, we can get a further reduction of 15 minutes in the runtime. We reduce the disk space measurably by about 150 gigabyte, and we further have a reduction in the I/O. So, also another part I would like to mention is that if you compare the amount of, what you see here in different colors is the amount of time that we use for the fatigue analysis, the time for the vibration analysis, and the time for the time history. The time for the fatigue analysis includes the reconstruction of the nodal point stresses, so we have to recompute the from the MLDR tree the modes shapes, do the calculations of the nodal point stresses of the modes, and then do the on-the-fly computation of the stress history. So if you just have a look at the fatigue analysis part, which is doing the rainflow counting and damage computation, you will see that we have here a parallel efficiency of 27 out of the possible 28 for the one slot that we were using. So this part is highly parallelized and almost shows a perfect scaling. So as a summary, what we now would call a fully integrated fatigue analysis for us consists of the automatic handling of the prerequisites, which guarantees you that we're using minimal disk space and the minimal computational effort that is needed for the fatigue analysis, including the on-the-fly computation of the intermediate results. So you may understand this as the PERMAS solution computes a minimal data set from which the fatigue analysis or multiple fatigue analysis that you can do generates the data as needed, and then afterwards you get your damage result. So the new features that we are now introducing for the version 20 is the handling of shell elements, the simplified approach for defining an SN curve via the SN curve generator, new result items that will give you hopefully a better insight into the problem that you're dealing with. As always, you have high performance capabilities of PERMAS at your hands, and the general features that you should keep in mind if you think about using the fatigue analysis in PERMAS are that you can do multiple fatigue analysis in the same situation, which may help you to set up and include also complex workflows that otherwise were not possible without using lots of scripts. And there is no need for a stress export or import. You can do this, but our recommendation for this would be to just store your displacements and recompute your stresses as needed if you're doing a fatigue analysis. So we try to encourage you, try it out, get in touch with us, and share your workflow so that we can help you improve your PERMAS experience. I thank you for your attention and hope you enjoy your evening, and please ask questions.
Are there any questions? Markus, please.
You said when you're in one situation you can change the material. I guess that is only the fatigue properties that you then change. So if you want to change really a material class, let's say you want to test gray cast iron or nodular cast iron or CGI, then you really have to change situations, system behind, and so on, correct?
As long as you can ensure that the stress data that you have computed is still in close agreement with the different material you're choosing, you do not have to redo the analysis.
Okay,
So
means
the
E modulus change means
so yeah, as soon as your modulus of elasticity changes, you have to redo your stresses. Otherwise, there's no need to do so.
okay.
More questions? We have time for.
Is there a limit of jobs I can handle in this numbers? Maybe I will see 3. Can we do 100?
Of the
If I
fatigue
have-
analysis?
Yes, of the fatigue analysis.
I mean, as I've already shown you in this case here, this was 70 fatigue analysis within one job. So we have not tried more than 70 so far, but you can do an arbitrary number. So there's no theoretical limit on why you shouldn't do thousands of fatigue analysis within one job or situation.
Okay, thank you.
I still would like to know the use case for this.
No, it's only a question because I'm surprised by other things that they explain there's no limit and then test it and then I find a limit. So if you can say say something in before, I have no stress. So it's
Okay.
Always find the disk limit.
yeah, for me sure. For me, sure.
Yeah, yes, I think it's possible to find a limit. That's a message. More questions? A typical question I asked, on which FKM this is based? There are so many.
Yeah, so far we have based this on the last, so this is the FKM guideline 7 from 2020, I think.
Okay, thank you. More questions? If here for one moment.
So there is also this new plastic deformation FKM, if you heard about it. So it takes care of cases where you have plasticity involved and enables you to compute fatigue for those cases.
So far we have not looked into this.
Okay. Thank you.
So if there is no question, thank you again, Erik, for this detailed presentation. Thank you.